Welcome to Nightwatch Observer. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've carried this little glow of a screen into, I'm glad you found your way to us. So before we begin, let me ask you the question I always like to ask. Where in the world are you watching from tonight? Are you somewhere cold with the heating ticking softly in the walls and a blanket pulled up to your chin? Are you on a train watching the dark slide past the window in long unbroken ribbons? Maybe you're on a couch you've half fallen asleep on 100 times before, with one lamp still burning in the corner of the room because you weren't quite ready to turn off the last of the light. Wherever you are, settle in. You don't need to sit up. You don't need to follow every word. The ideas will still be here in the morning, exactly where we left them. And if you enjoy these slow journeys into the dark and you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little corner of the internet keep going. Small channels like this one rely on it more than you'd think. And to those of you who've already subscribed, who come back night after night to let me talk you towards sleep, thank you, truly. You're the reason the Nightwatch keeps watching. Now I should warn you, tonight's story is a strange one. It's about a death that wasn't an accident. It's about a machine far away in the dark that we built and loved and then chose to destroy on purpose. And it's about what that machine found in the very act of dying. So I'll make you the same promise I always make. I'll try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something. Fair trade, I think. Let me start with something I'd like you to just sit with for a moment before we explain a single thing about how we know it. It's a fact so quietly enormous that I think it's worth letting it land slowly, the way a stone settles to the bottom of a still pond. The rings of Saturn, those vast, shining hoops of ice that you've seen in 1,000 pictures, the most famous feature of any planet in our whole solar system. Those rings may be young, not young the way we usually mean it, not young like a few centuries or a few thousand years. Young in a way that's almost impossible to feel in your bones. The rings may be only about 100 million years old, perhaps a little more, perhaps even less. And here's why that number is so strange. Saturn itself is old. The planet has been turning out there in the dark for about 4.5 billion years, almost as long as the sun has been shining. 4.5 billion, 100 million. Tip those two numbers against each other and you start to feel the dizziness of it. The rings, it seems, were not there for most of Saturn's life. The planet spent billions of years barefaced, ringless, just a great striped ball of gas turning in the cold. And then comparatively recently, almost yesterday in the long calendar of the universe, the rings appeared. Let me put it another way because I think it's the kind of thing your mind wants to hold on to as you drift. There were dinosaurs walking on the Earth. Heavy-footed, long-necked creatures moving through warm green forests under a sky much like ours. And it's entirely possible, genuinely possible, that during all of that Saturn had no rings at all. That the rings we think of as ancient and eternal formed after the dinosaurs were already here. A creature could have looked up at the night sky from a Jurassic riverbank and seen Saturn as nothing more than a dim, plain, unremarkable dot. No rings. Not yet. It's a beautiful thought, isn't it? And a slightly unsettling one too, if you let it be. Because it means those rings are not a permanent fixture of the heavens. They're a passing thing, a phase. Something that arrived and that will one day leave again. Now here's a second fact to set beside the first, and I want you to picture this one as plainly as you can, because the picture is half the point. Those rings stretch out from the planet for an enormous distance, tens of thousands of miles of them, ring after ring after ring, a structure so wide you could lay the distance between the Earth and the Moon across it. It looks, in every photograph, like one of the most massive things in the solar system. Acres upon acres of bright material going on and on. And yet, if you could somehow gather up all of that ring material, every last shimmering particle of it, scoop the entire ring system into one enormous pile and weigh it, do you know how much it would come to? Less than half the weight of one small moon. A little moon called Mimas, which is itself only about 400 kilometers across, a modest, icy ball you could drive across in a day if there were roads on it. All those rings, all that breathtaking width, all that brightness, and the whole lot together weighs only about 4/10 of tiny Mimas. It's a bit like discovering that a cloud which fills the entire sky, horizon to horizon, weighs less than a bucket of water. The grandness is an illusion of spreading. The rings are vast and thin and almost weightless, a great gossamer sheet of frost flung out around the planet. And that lightness, as we'll come to see, is one of the very clues that tells us how young they are. So that's where we're going tonight, to the rings of Saturn, and to the strange truth that they are young, and that they are thin, and that they are not going to last. But to get there, we have to talk about the machine that found all of this out. And we have to talk about the way that machine died. Because here is the thing I find almost too neat to be real, the thing that sits right at the heart of this whole story. The death and the discovery were the same act. We didn't lose the spacecraft and then separately learn these things. The very maneuver that destroyed it was the maneuver that taught us. It died learning. Or rather, it learned by dying. I'll explain exactly what I mean by that slowly in a little while. For now, just hold the shape of it in your mind. One act, death and discovery, folded together into a single thing. Let me tell you about the spacecraft. Its name was Cassini. The full name of the mission was Cassini-Huygens because it was really two travelers in one. There was the main spacecraft, Cassini, about the size of a small school bus, bristling with instruments and cameras and antennas, and riding on its side, like a passenger clinging to the back of a much larger animal, there was a smaller probe called Huygens, built to be dropped off at a particular destination once they arrived. Two names, two machines, one journey. Cassini left the Earth on the 15th of October in the year 1997. Sit with that date for a moment because it tells you something about patience. 1997, a different age, almost a different world. And the spacecraft didn't simply fly straight to Saturn because you can't. Not really. Saturn is so far away and the energy needed to reach it so enormous that the engineers had to be clever. They sent Cassini looping through the inner solar system first, swinging past Venus, past the Earth again, past Jupiter, using the gravity of those worlds like a series of slingshots, each pass flinging it a little faster and a little farther out into the dark. It took the long way round on purpose. It gathered its speed in patient, looping increments. And so it was not until the 1st of July in the year 2004, almost 7 years after it left home, that Cassini finally arrived. 7 years of crossing the emptiness, 7 years of falling silently through a dark so complete and so cold that nothing we have words for can really describe it. And then at last, Saturn. The spacecraft fired its engine to slow itself down just enough to be captured by the planet's gravity, to slip into orbit rather than sailing helplessly past. That maneuver is called orbit insertion, and it's exactly what it sounds like. You insert yourself into orbit. You arrive and you stay. And stay it did. For about 13 years, Cassini circled Saturn. 13 years. Think about how much of a life that is. Children were born and started school in the time Cassini spent looping around that distant world. It crossed and recrossed the planet's neighborhood hundreds of times, threading between the moons, dipping close to the rings, swinging far out, and then back in again, patient and tireless. Across the whole of its journey, from launch to its final moment, the mission lasted about 20 years and traveled something like 4.9 billion miles. Was 5 billion miles. The number is so large it stops meaning anything, which is the trouble with these numbers. So don't try to feel the whole of it. Just feel a fraction. Just feel that this small machine traveled farther than you could travel in 1,000 lifetimes of driving and kept working the entire way. And what did it do with all that traveling? It looked, it listened, it tasted the dust and the gas around it. Over its lifetime, Cassini sent home something like 453,000 images, almost 500,000 photographs of a world no human eye has ever seen up close. Pictures of the rings lit from behind by the sun, glowing like a halo. Pictures of storms the size of continents, churning through the planet's clouds. Pictures of moons you'd never heard of, little frozen worlds with names like poetry. And early on, in the January of 2005, Cassini did the thing it had carried that little passenger probe all this way to do. It released Huygens. The small probe fell away from its larger companion and dropped down through the thick orange haze of Saturn's biggest moon, a place called Titan, and it landed there, gently, on a surface no machine had ever touched. That was the first time anything we had ever built came to rest on a world in the outer solar system. The first landing out there in the far dark, past the asteroids, past Jupiter, all the way out at Saturn. A small probe settling onto an alien shore and sending back for a little while what it could see before the cold and the silence took it. We'll come back to Titan later because it matters a great deal to our story, more than you'd guess. But for now, just hold the picture. A thing we made resting on the ground of another world, almost 1 billion miles away. I should say, too, that Cassini was not the work of any one country. It was built and run by many hands across the world. The American Space Agency, NASA, working through its laboratory in California, the Jet Propulsion Laboratory, often just called JPL, and the European Space Agency, ESA, which built that little Huygens probe that landed on Titan, and the Italian Space Agency, known as ASI, which built one particular piece of the spacecraft that will turn out to be surprisingly important to how this story ends. A great dish-shaped antenna, the high-gain antenna, the main way Cassini spoke to the Earth across all those billions of miles. Remember that antenna. We'll need it again before the night is through. So there it is, our traveler. Launched in 1997, arrived in 2004, working faithfully for 13 years at Saturn, 20 years in all. Almost 5 billion miles of journey, nearly 500,000 pictures sent home through a dish built in Italy. A machine that did everything we asked of it, and more. And then on the 15th of September, in the year 2017, at about 5 minutes to noon in Coordinated Universal Time, we destroyed it, on purpose. Let me say that again gently, because I know it's the kind of thing the mind slides past on first hearing. We did not lose Cassini to an accident. It did not break down, it did not run into something or drift away or fall silent on its own. It was working, the cameras still worked, the instruments still worked, the radio still spoke clearly across the dark. By every ordinary measure, it was a perfectly healthy, perfectly functional billion-dollar machine, and we deliberately steered it down into the clouds of Saturn and let it burn. It fell into the upper atmosphere of the planet, and it burned up there like a meteor, like a shooting star, the way a grain of dust burns when it streaks across the night sky over your head. The friction of the gas tore at it and heated it until it glowed and broke apart and scattered into the great striped body of the planet it had studied for so long. The last of its signal reached the Earth that morning, and then there was nothing. The radio that had spoken for 20 years went quiet and stayed quiet and will be quiet forever. Now the natural question, the one I imagine forming somewhere at the edge of your half-sleeping mind, is simply this: why? Why would anyone do that? Why take a working spacecraft, a thing of such expense and such genius, a machine that had crossed 5 billion miles and never once failed, and throw it deliberately to its death? It seems almost cruel. It seems wasteful. There must be a reason, and there is, and it is one of the most quietly moving reasons I know of in all the history of exploration. But I want to be careful here, because there is a lazy way to tell this part, and I don't want to tell it the lazy way. The lazy way is to say that Cassini died bravely, that it was a noble sacrifice, that the engineers wept in the control room as their little robot went out in a blaze of glory. And all of that is true in its way. There were tears in that control room. It was a kind of funeral. People who had given decades of their lives to this machine sat together and watched the signal fade and grieved, genuinely grieved, the way you'd grieve an old friend. That part is real, and it's tender, and we shouldn't pretend it isn't. But if that's all you take away, then you've missed the actual marvel of it, because the death was not just a sad ending tacked onto a happy mission. The death was the experiment. The way Cassini died was itself one of the greatest scientific acts of the entire 20-year journey. The funeral and the discovery were the same event. And tonight, I want to take you slowly, carefully, into why that's true, because once you see it, you can't unsee it. And it changes the whole shape of the story from something sad into something far stranger and far more beautiful. So let's begin with the why we had to do it at all. Here's the simple version, and then we'll deepen it slowly. By the year 2017, Cassini was running low on fuel. Not the fuel that moves it through space exactly, but the propellant it used to control which way it was pointing, to turn, to aim its cameras, to keep its antenna facing the Earth so it could keep talking to us. A spacecraft needs to nudge itself this way and that with little bursts of gas. And that gas was nearly gone. Once it ran out, Cassini would become uncontrollable. It would still be there, still circling Saturn, but it would be a deaf, blind, tumbling thing, drifting wherever physics carried it, unable to point, unable to steer, unable to listen. And that, it turned out, was a genuine danger. Not to us. We were never in any danger from a small spacecraft drifting around Saturn. The danger was to something else, something Cassini itself had found. You see, in the years it spent at Saturn, Cassini made a discovery that changed everything about how we think of that distant system. It found, around one of Saturn's moons, the conditions for life, not life itself. I want to be very precise about that because it's the kind of thing that gets exaggerated, and the truth is stunning enough without exaggeration. Cassini did not find life, but it found a place where life, as far as we understand it, might be possible. And once you've found a place like that, you carry a terrible responsibility. You must never, ever be the one who poisons it before anyone has the chance to look properly. And there it is, the heart of the whole thing, the reason that turns the death from a tragedy into something almost unbearably fitting. Cassini had to be destroyed precisely because of what Cassini had discovered. The moon it died to protect was a moon it found itself. It uncovered a secret, and the uncovering of that secret was its own death sentence. We had to make sure that this uncontrollable tumbling machine with no fuel left to steer it away could never one day drift down and crash into that fragile, possibly living place and contaminate it with whatever earthly microbes might still cling to its metal after 20 years in space. So we chose instead to send it somewhere it could do no harm. Down, into Saturn itself, into a great deep ocean of crushing gas where nothing could survive, where the spacecraft would simply burn away to nothing and be gone. A clean death, a safe death, a death chosen so that something else might be allowed to live, or at least to be discovered properly by the gentler hands of the future. I find that almost impossibly moving, and I think you will too, once we've sat with all the pieces. A machine that found a possible cradle of life and then was deliberately killed so that it could never spoil that cradle. It's the kind of decision that I think says something rather good about us, about the people who plan these things, that we would take a perfectly working spacecraft and end it willingly, out of care, for a world that may or may not hold anything alive at all, out of a kind of cosmic politeness, out of the simple principle that you do not muddy the water before anyone has had a chance to drink. We'll get into exactly what Cassini found around that moon, and which moon it was, and why we believe what we believe about it. We'll get into the rules that govern this sort of careful destruction, rules written down in treaties decades ago, long before we had a spacecraft this far out to worry about. And then once all of that is in place, we'll get to the part I keep promising you, the death that was also the discovery. The 22 final dives threaded through a gap no machine had ever crossed, that let us reach out and weigh the rings of Saturn for the very first time, and learn that they are young and learn that they are dying. But before any of that, I want to take you all the way back, much further back than 1997, to set the scene properly. Because to understand why the youth of the rings is such a shock, you have to understand how long we believed the opposite. You have to feel the weight of the old, comfortable, wrong idea before the new one can knock it over. For most of the history of astronomy, nobody even knew the rings were there. They're far too faint and far too distant to see with the naked eye. They were a secret the universe kept from us entirely until we built the right tools. The first person to point one of those tools at Saturn was Galileo, the Italian astronomer, in the year 1610. He had one of the very first telescopes, a crude little tube of lenses, wonderful for its time but feeble compared to anything we'd use today. And when he turned it towards Saturn, he saw something he could not make sense of. The planet did not look round and clean the way the others did. It seemed to have something on either side of it. 2 bumps, 2 lumps, as if Saturn had grown a pair of ears, or as if it were not one body but 3, a large one in the middle with a smaller one stuck to each side. He didn't have the clarity to see that those bumps were a ring. His telescope simply wasn't sharp enough to resolve it. So he described what he saw as best he could, this strange triple shape, these ears, and he puzzled over it without ever quite solving it. It took another 45 years and a better telescope for the answer to come. In the year 1655, a Dutch astronomer named Christian Huygens, the very same Huygens whose name we gave to that little probe that landed on Titan, looked again with sharper eyes and finer lenses, and he understood. Saturn was not a triple body. It did not have ears. It had a ring. A thin, flat, encircling ring set around the planet without touching it. A halo of something hung in the dark, and from that moment on, for centuries, the assumption settled into place, quietly, without anyone ever really questioning it. The rings were simply part of Saturn. They were what Saturn was. A ringed planet, ringed presumably from the very beginning, ringed the way it had always been and always would be. Why would anyone think otherwise? When the planet formed all those billions of years ago, surely the rings formed with it, leftover scraps from the same swirling cloud of material that built the whole system. They were old, they were original, they were as ancient as Saturn itself. 4.5 billion years of frost held in place eternal as anything could be. That was the settled view, that was the comfortable truth that astronomers carried in their minds for 3.5 centuries, from Huygens all the way down nearly to our own time. The rings are old, the rings have always been there, the rings will always be there. It felt obvious, it felt safe. It was the kind of thing you simply assumed and never bothered to check, because how on earth would you even check it? How could you possibly find out how old a ring is, hundreds of millions of miles away, made of countless tiny pieces of ice, just by looking at it from afar? And that, my friend, is exactly the question. That's the locked door. For 350 years, it stayed locked because there was no way through it. You cannot age the rings from a distance. You cannot weigh them with a telescope. To know how old they really are, you would have to get close, impossibly close. You would have to fly inside them into the narrow gap between the rings and the planet, into a place no spacecraft had ever dared to go, and weigh them directly by feeling their pull on your own body as you fell, which is precisely, exactly what a dying spacecraft with the last of its fuel and nothing left to lose was finally sent to do. But let's not run ahead of ourselves. We have all night, and there's no rush at all. Let me take you back to the very beginning of this strange story, because to understand the death, you first have to understand the life. And what a life it was. Its name was Cassini, or to give it the full, proper name, Cassini-Huygens, two halves of one machine. The larger orbiter named for an old Italian astronomer, and a smaller probe tucked against its side, named for the Dutchman who first understood what those ears really were. Together they made up one of the most ambitious things our species has ever flung into the dark. It left Earth on the 15th of October, 1997. Picture that for a moment wherever you're lying tonight. 1997. A long time ago now, and from that autumn launch, it began the slowest, most patient kind of journey imaginable, a journey not of days or weeks, but of years, looping out through the inner solar system, borrowing little tugs of gravity from Venus, then Venus again, then Earth one last time, then mighty Jupiter, each world giving it a gentle push, flinging it a little farther out toward the cold. Nearly 7 years it traveled, almost 5 billion miles before it was done. 4.9 billion to be precise, which is a number so large it stops meaning anything, a number you can't really feel, so don't even try. Just let it be big, let it be impossibly, beautifully big, and let it go. And then, on the 1st of July 2004, after all those years and all those miles, it arrived. It slipped into orbit around Saturn, threading itself through a gap in the rings, firing its engine to slow down just enough to be captured by the giant planet's gravity. And there it stayed, not for a day, not for a year. For 13 years it circled Saturn around and around, a tiny, faithful machine in orbit about a world over 800 million miles from home. 13 years. Think about everything that happened in your own life across 13 years, and the whole of that time, this little robot was out there in the dark and the cold, working, watching, never once coming home. 20 years, all told, from launch to the very end. 20 years of one machine's life, spent almost entirely in the deep silence between the worlds. And in those 13 years at Saturn, it sent back roughly 453,000 images, nearly 500,000 photographs of a place no human eye will likely ever see in person. It dropped its little Huygens probe down onto the surface of Titan, the first and only landing humanity has ever made in the outer solar system, on a frozen moon with rivers and seas of liquid methane. It discovered new moons. It found things nobody had dreamed were there. It was not, you understand, the work of one country alone. It was a gift built between many hands. NASA through its Jet Propulsion Laboratory, the European Space Agency, and the Italian Space Agency, ASI, who built the great dish antenna it used to whisper its findings back across the void, an antenna that would matter at the very end in a way nobody quite expected. So here is a thing worth sitting with quietly as you start to drift. A spacecraft that took 7 years to arrive and worked for 13 more. A billion-dollar machine, still healthy, still listening, still doing exactly what it was built to do. And then, on a September morning in 2017, the people who had spent their whole careers tending it, who loved it the way you might love something you'd raised, gave the command to fly it straight down into Saturn and burn it to nothing. On purpose, deliberately, with full knowledge of exactly what they were doing. The 15th of September 2017, at around 11:55 in the morning, by the clock the world agrees to share, Cassini plunged into the upper layers of Saturn's atmosphere and was torn apart by the friction, glowing like a falling star, scattering into the very planet it had studied for so long. Gone. A working spacecraft destroyed by the very people who built it and ran it and cared for it more than anyone. And the question that hangs over all of this, the question I want you to carry softly down into sleep with me, is the simplest one of all. Why? Why would anyone do that? Why kill something that still works? Why burn up a machine worth $1 billion when it was still answering every call, still sending its pictures home? The easy answer, the one you'll hear most often, is the sad and gentle one, the brave little robot out of fuel, sent out in a blaze of glory, a funeral in the sky, and there's truth in that, there really is, and we'll honor it before the night is through. But it is not the real answer. It is not why. The real reason is stranger and far more beautiful, and it ties the death of this spacecraft to a discovery that the spacecraft itself had made years earlier with its own instruments. Because here is the quiet, astonishing heart of the whole thing. Cassini was not destroyed in spite of what it found. It was destroyed because of what it found. The death and the discovery are not two separate stories. They are one single act, folded together, inseparable. The very thing that killed it is the very thing that let it weigh those ancient rings and learn the secret they'd kept for 4.5 billion years. But I'm getting ahead of myself again. We've a long, slow way to go yet, and I'd much rather we wandered there gently. If you're enjoying drifting through this with me, a quiet like and a subscribe genuinely help this sleepy little channel keep going. Small creators like me really do rely on it, more than you might think, and I'm grateful to every one of you who's already here. No need to do anything now, of course. Just let it be a thought at the edge of your mind, like leaving a lamp on low in the next room. And I'd love to know, while you're settling in tonight, where in the world are you listening from? What time is it in your corner of the night? It's a lovely thing to imagine, all of us scattered across the dark, listening to the same slow story. So let's go back to that ocean, because that's where the why begins. Years before the end, long before anyone was thinking about how this mission would die, Cassini was simply doing its job, sweeping past the moons of Saturn, photographing them, measuring them, getting to know each strange little world in turn. And one of those worlds was a small, bright, icy moon called Enceladus, barely 300 miles across, a frozen pebble, you'd think, dead and still and silent, the kind of place you'd glance at once and never think about again. It was not dead, it was not still, and what Cassini found there would, years later, become the very reason it had to die. It was the year 2005. Cassini was making one of its early close passes by Enceladus, cameras and instruments turned patiently toward that small, brilliant sphere. And then the data started coming back, and the scientists looking at it could barely trust what they were seeing. From the south pole of Enceladus, from a region laced with long, parallel fractures in the ice, fractures the team would soon call the tiger stripes, something was erupting. Not explosively, not violently, more like a breath held for a very long time, finally released. Water vapor and tiny particles of ice were venting up from those cracks in enormous feathery plumes, rising hundreds of miles above the surface and then dispersing into space, seeding the outer edge of Saturn's E-ring with fresh, clean ice grains. Take a moment and picture that. A moon only about 300 miles across, smaller than the state of Texas, smaller than some mountain ranges on Earth, quietly exhaling a geyser of water vapor into the cold dark of the outer solar system. The pressure beneath those fractures had to be enormous. The heat driving it had to come from somewhere deep. And water vapor rising from inside a moon means one thing above almost anything else: liquid water. Not ice, liquid. Somewhere beneath that frozen crust, beneath miles of ice, Cassini's data was pointing toward a body of liquid water, a subsurface ocean, hidden and warm and dark and strange. The tiger stripe fractures were the cracks where that ocean was breathing, where the pressure from below was finding a way out, pushing water up through the ice and into space in long, graceful plumes. And this was not a small finding. This was not a footnote. This was one of the most stunning discoveries in the entire history of planetary science, sitting quietly in the data coming back from a small moon most people had never thought about. Because here is the thing about liquid water. Everywhere on Earth, everywhere, without exception, wherever there is liquid water, there is life. Deep in the ocean, in water so hot it would scald you, in acidic pools where nothing seems like it should survive, in water pockets buried miles beneath Antarctic ice, life finds it. Life clings to it. Life appears to be almost alarmingly creative when it comes to making use of liquid water. So when an instrument in the outer solar system returns data pointing to a hidden subsurface ocean, the question that arrives with it is enormous and thrilling and slightly terrifying. Could something be living there? Cassini couldn't answer that, not yet, not in 2005, but it kept looking. And over the following years, as it made more and more passes by Enceladus, as its instruments grew more precise in their attention to that plume, the data kept piling up. And by 2017, published in the journal Science that April, a team led by J. Hunter Waite had found something inside that plume that took the question about life and pushed it from the merely possible toward the genuinely urgent. Molecular hydrogen, H2, free hydrogen gas, venting out of Enceladus right along with the water vapor and the ice. Now, molecular hydrogen on its own is not unusual, but molecular hydrogen rising out of a moon's interior, together with water, in steady, continuous quantities, that tells a specific story. On Earth, there is a process that happens at the bottom of the ocean, in places where the tectonic plates are pulling apart and hot rock is exposed to cold seawater. The water reacts with the rock in a chemical process called serpentinization, and one of the byproducts is molecular hydrogen. And where that hydrogen wells up from the seafloor, communities of microorganisms gather, feeding on the chemical energy it provides. These are hydrothermal vents. These are the places where life does not need sunlight at all, does not need the surface, does not need photosynthesis, because it has found a completely different energy source buried in the chemistry of hot rock meeting cold water. The molecular hydrogen in Enceladus's plume, combined with everything else Cassini had measured, was consistent with exactly that. With hydrothermal activity on the floor of that hidden ocean, with hot water chemistry happening in the dark, down where the rock met the sea, generating the kind of chemical energy gradients that, on Earth, feed entire ecosystems. To be careful, and we should be careful because this is science, not speculation, what Cassini found were the ingredients the conditions, not life itself, not a single microorganism, not a protein, not a cell. What it found was a place that has liquid water, a chemical energy source consistent with hydrothermal activity, and, detected in that plume as well, organic molecules, carbon-bearing compounds, the building blocks of the chemistry from which life, as we know it, is assembled. Liquid water, an energy source, organic molecules. Three of the most important boxes on the checklist that astrobiologists use when they ask where in the universe life might be possible. Enceladus was checking them, quietly, under the ice. In the outer solar system, more than 1 billion kilometers from the Sun. And then there is the question that follows all of this naturally, the question that arrived in the minds of the people responsible for Cassini as they looked at what it had found. What do we do about it? Because the mission would not last forever. Spacecraft never do. They carry fuel and fuel runs out. By 2017, 13 years after arriving at Saturn, Cassini was approaching the end of its propellant reserves, the hydrazine and the oxidizer it used to fire small thrusters and maintain control of its orientation. When those reserves were gone, Cassini would no longer be able to point itself reliably, no longer be able to make precise maneuvers. It would be, in effect, a drifting object in the Saturn system, a drifting object with no guidance, no brakes, and a very long history in a system full of interesting things to crash into. The people at NASA and JPL had known this moment was coming for years. The question of what to do with Cassini when its fuel ran low had been a real engineering and ethical question that had been building slowly in the background throughout the entire mission. And the answer that planetary protection demanded was not comfortable, but it was clear. Cassini had to be destroyed. Planetary protection is a doctrine. It sounds bureaucratic when you say it that way, and in some respects it is. It has its committees and its categories and its official guidelines, but at its core it is a simple and serious idea. When we send spacecraft to other worlds, we do not want to bring our biology with us. Earth is saturated with microbial life. Every spacecraft that leaves this planet, no matter how carefully it is cleaned, carries the possibility of carrying along microscopic stowaways, bacteria, spores, the hardy survivors of terrestrial life that can endure vacuum and radiation and cold in ways that are frankly astounding. If one of those stowaways were to arrive on a world that might already host its own biology, we would have no way of ever cleanly separating what was native from what we brought. The lineage of this concern goes back further than most people realize. The Outer Space Treaty of 1967, one of the foundational documents of the space age, signed by over 100 nations, includes, in Article 9, an explicit obligation. Countries party to the treaty commit to pursuing exploration of celestial bodies in a manner that avoids their harmful contamination. That principle was translated into operational categories by COSPAR, the Committee on Space Research, which assigns levels of protection based on how likely a target world is to harbor life and how damaging contamination might be if it did. The moons of the outer solar system, particularly those with evidence of liquid water, sit at the highest levels of concern. In practical terms, when Cassini was launched in 1997, Enceladus was not yet known to be an ocean world. It was just a small, icy moon, rated for relatively modest planetary protection precautions. But Cassini itself changed everything Cassini knew about Enceladus. And once that plume was discovered, once the data pointed toward a subsurface ocean with hydrothermal chemistry, Enceladus moved into a different category altogether. It became a place that might harbor life, which meant it became a place that Earth microbes must never be allowed to reach. And there was Cassini, powered by 3 radioisotope thermoelectric generators using plutonium-238, carrying whatever microscopic terrestrial life had survived the journey, running low on the propellant it needed to control itself, circling Saturn, just a few careful maneuvers away from Enceladus. If Cassini was simply abandoned, left to drift when its fuel ran low, it would eventually, possibly within decades, possibly longer, be pulled by the complex gravitational choreography of Saturn's moons into a collision with one of them. There was no guarantee it would hit Enceladus specifically, but there was no guarantee it wouldn't. And in planetary protection, that kind of uncertainty is not acceptable. The probability does not have to be certain. The possibility is enough. Because if we contaminate a world that actually hosts indigenous life, we may never be able to undo that. We may never even know that we did it. Titan raised its own concern. Titan is Saturn's largest moon, a world so strange and so rich that it required its own probe. The Huygens lander, carried to the Saturn system by Cassini and released to descend through Titan's atmosphere on January 14, 2005, becoming the first spacecraft ever to land in the outer solar system. Titan has a thick nitrogen atmosphere, one of the only bodies in the solar system other than Earth with a dense nitrogen sky, and on its surface, pooled in low-lying basins and carved into channels by slow-moving rivers, are stable liquids, not water because Titan is far too cold for liquid water on its surface, but methane and ethane, hydrocarbons, gathered into lakes and seas. Kraken Mare, the largest, is thought to be comparable in size to Earth's Caspian Sea, possibly larger. Ligeia Mare is another. Cold, still, dark hydrocarbon seas sitting quietly under an orange haze. Whether anything could live in those methane seas is a very different and very open question from the warm water hydrothermal argument for Enceladus. The chemistry would be so exotic, so different from anything we know on Earth, that nobody is certain whether life of any kind could take hold there. But the uncertainty itself is enough. Titan is strange and potentially significant, and the possibility that it harbors some form of chemistry on the road to life, or already there, could not be dismissed. So Cassini, drifting uncontrolled near Titan, also unacceptable. And then there is the matter of the power source. Cassini's 3 radioisotope thermoelectric generators, RTGs as engineers call them, used the slow radioactive decay of plutonium-238 to generate heat and converted that heat into electricity. It is a beautiful, reliable system for a spacecraft going somewhere the sun is too faint to power solar panels. And it worked perfectly for Cassini throughout its entire mission. But plutonium-238 is obviously radioactive. If Cassini were to impact a moon uncontrolled, not only would it carry Earth biology to that moon's surface, it would also deliver its RTG material in an uncontrolled impact. A clean, deliberate incineration in Saturn's upper atmosphere, burning up completely, becoming part of the planet itself, was far preferable. Saturn is vast and ancient and already contains within it more complex chemistry than we can fully account for. Cassini falling into Saturn, completely disintegrated, was a clean and controlled ending. All of these threads converge on the same conclusion: a spacecraft that was running low on fuel that might drift into a life-bearing or potentially life-bearing moon that carried plutonium and terrestrial biology had to be guided precisely and intentionally into Saturn, had to be burned up. The mission team had years to plan it, to think through every detail, and when the time came, the plan they chose was not just an ending, it was, and this is the part the standard telling often soft pedals, also one of the most scientifically productive phases of the entire mission. Because to get Cassini to Saturn in a way that would incinerate it cleanly, they had to fly it through somewhere it had never gone before, somewhere nobody had gone. That necessity, that forced geometry, is what transformed a controlled disposal into an experiment, and that experiment is the one that rewrote everything. But there is something underneath all of this that deserves a moment of quiet attention before we move on, something that is almost too strange to sit with comfortably. Cassini did not discover Enceladus. It had been known since 1789 when William Herschel identified it through his telescope. But no one had any real reason to think it was anything more than a small, icy, dead moon until Cassini arrived and looked closely. It was Cassini's instruments, Cassini's cameras, Cassini's passes close to the surface that found the tiger stripes, that found the plumes, that returned the data pointing toward a liquid water ocean beneath the ice, that measured the molecular hydrogen suggesting hydrothermal chemistry in the dark below. Cassini found the ocean that made Cassini dangerous. Cassini created the reason for its own destruction. Think about that for a moment. The spacecraft sent to explore the Saturn system arrived there, did its job faithfully and brilliantly, and in doing so discovered that one of the things it was exploring was too important, too precious, too potentially alive to be allowed to be contaminated by the spacecraft itself. Cassini's success was the argument for Cassini's death. There is something genuinely poignant about that if you let yourself feel it. A machine built and launched and guided across 4.5 billion miles of space, spending 13 years in the Saturn system sending back knowledge we had never had, and then finding something so significant that the only responsible thing to do was to destroy the finder. Not because it had failed, because it had succeeded. There were people in mission control who had spent decades of their working lives on Cassini. Scientists and engineers who had been graduate students when the mission launched and had grown into senior researchers during the years at Saturn. People for whom the final signal received at 7:55 in the morning, Pacific time on September 15, 2017, was not just the end of a data stream, it was the end of something they had given a significant portion of their lives to. The emotion in mission control that morning was real, and it was visible, and it was entirely human. Cassini was not alive. It did not know it was dying. It had no sense of the significance of what it was doing, but the people behind it did, and the love they had for that machine and what it had taught us was entirely real. The mission was international, worth saying clearly. NASA led it through the Jet Propulsion Laboratory in California. The European Space Agency was a full partner, contributing instrumentation and, critically, the Huygens probe that descended through Titan's atmosphere. The Italian Space Agency, ASI, built the high-gain antenna, the large dish that Cassini used to communicate with Earth across that vast distance. That same dish, as it turned out, would serve one more function in the mission's final months. But we will get to that. What matters here, in this part of the story, is the logic, the chain of consequence that runs from a discovery to a death. In 2005, Cassini found water vapor venting from the south pole of Enceladus. That discovery, followed by years of increasingly detailed measurements, eventually revealed a subsurface ocean with what appeared to be hydrothermal chemistry. The conditions, not the confirmation, but the conditions under which life as we know it might exist. That finding elevated Enceladus to a place of paramount astrobiological importance, which meant Enceladus had to be protected, which meant Cassini, running low on fuel and potentially drifting, could not be allowed to accidentally contaminate it, which meant Cassini had to be deliberately guided away from every moon and into Saturn itself. And the route chosen for that guidance, the specific orbital geometry of the grand finale, was not just the path of least harm, it was the path of greatest discovery. The same trajectory that kept Cassini away from Enceladus and Titan and every other moon, the same path that committed it to incineration took it through the one region of the Saturn system that no spacecraft had ever explored, the gap between the rings and the planet, the 200-mile corridor between Saturn's cloud tops and the inner edge of the D-ring. 22 times, and what it found there, what it measured in those 22 passes, before its final plunge, is the other half of this story. The half that answers the question the title quietly promises, the half that actually rewrote Saturn. But we are not quite there yet. Planetary protection is not a vague sentiment. It has architecture. The Outer Space Treaty gave it a legal foundation in 1967, and over the decades that followed, the Committee on Space Research translated that foundation into operational guidance. COSPAR's categories run from Category 1, bodies with no interest for understanding the origin of life, minimal precautions needed, all the way to Category 4 and V, which apply to worlds where life might exist, or where samples returning to Earth could contaminate our own biosphere. The exact category assignment for Enceladus shifted after Cassini's discoveries. A moon that was assumed cold, dead, and geologically inert when Cassini launched was reassigned when the data from those early passes came back. This is how science and policy interact in real time. The mission created the data that created the ethical constraint that shaped the mission's end. There are people who might find this frustrating. A working spacecraft, still functional, still capable of returning science, deliberately destroyed because of a rule about contamination, a contamination risk that would have to involve a very specific and still hypothetical chain of events. But this is the right way to think about it. The value of the protections comes precisely from the fact that they are firm. A planetary protection policy that bends when it's inconvenient is not a planetary protection policy. It is a suggestion. And if we ever contaminate Enceladus, if Earth microbes reach that ocean, perhaps surviving the journey, perhaps even thriving, we will not necessarily know that we did it. We might send a future mission, find biology, and never be able to say with certainty whether what we found was native to Enceladus or arrived on a spacecraft from Earth. The contamination would not just be biological, it would be epistemological. We would lose the ability to know. So the decision was firm, and it was right. And it was not, in the end, a sacrifice of science. It was, as we are slowly coming to, a redirection of science into the only path that could produce what the mission produced in its final months. There is one more element of the planetary protection calculation worth sitting with for a moment, and it has to do with the nature of the RTG power source. Plutonium-238 decays by emitting alpha particles, a type of radiation that is relatively easy to shield against but still dangerous in quantity. The 3 RTGs aboard Cassini had been generating steady, reliable power since the spacecraft launched in October 1997, 20 years of operation. By 2017, the plutonium had decayed enough that the power output was lower than it had been at launch, but the RTGs were still working, they were still warm, and they were still radioactive. An uncontrolled crash landing on Enceladus or Titan would not just carry terrestrial microbes, it would deliver those RTGs at impact velocity. The consequences are not fully predictable, but they are not neutral either. A clean incineration in Saturn's upper atmosphere at the temperatures and pressures of a planetary atmosphere. Cassini would be completely destroyed, completely integrated into Saturn, reduced to its component atoms, and absorbed into a planet so massive that its contribution would be immeasurable. That is a different outcome from a crater on a small moon. So the logic closes on itself from every direction. Biological contamination risk, radioactive material risk, the impossibility of controlling a fuel-depleted spacecraft, the astrobiological importance of the moons themselves, all of it pointed to the same answer. Cassini's ending was not negotiable. And once the ending was settled, the question became, how do we get as much science as possible out of the final months? How do we make the path to destruction also the path to discovery? The answer was the grand finale. And before we drift into it, there is just this to hold on to as you settle a little deeper into wherever you are tonight. Cassini spent 13 years at Saturn. It sent back more than 453,000 images. It discovered new moons. It revealed the depths and the chemistry and the geometry of a system that had been, for 4 centuries, little more than a bright point in a telescope lens with a ring around it. It delivered the Huygens probe to Titan's surface, giving humanity its first view from the ground of a world in the outer solar system. A haze, diffused orange landscape with rounded pebbles of water ice worn smooth by flowing methane. It found storms and hexagons and shepherd moons and the subtle dance of gravitational resonances that shapes every feature of those rings from the outside. And then, in the spring of 2017, it began its final act. The grand finale was announced: 22 orbits, a region no spacecraft had ever entered, and a date in September 2017 when the last data would return. What the team designed was not just a death, it was an experiment, the kind of experiment that could only be done by going somewhere nobody had gone before. The kind that required the trajectory that would also, incidentally, kill the spacecraft. The death and the discovery. One act, not two. Not far from your thoughts right now, I hope, as you drift a little further into the quiet, is that small icy moon with its tiger stripes breathing water vapor into space. A moon barely 300 miles across, sitting in the cold dark, harboring an ocean. The ocean Cassini found, the ocean that made Cassini dangerous, the ocean Cassini had to die to protect. Enceladus is still there. The plumes are still rising. The ocean is still dark and warm and hidden and unknown. And somewhere in that not knowing, there is still the question. The one Cassini could not answer. The one that will require another mission, another journey, another long, slow crossing of the space between here and there. But those are thoughts for a different night. Tonight, we are following Cassini's last orbits, into the gap, into the unknown corridor between the rings and the planet, into the place where the old assumptions about Saturn would, slowly and precisely and irrefutably, begin to give way. Take a breath. Let your hands relax. The story is still here, and there is no hurry. We are going somewhere remarkable. The gap had a name by the time it was done. The team called it the Big Empty. Before the first dive on April 26, 2017, nobody was entirely certain what lived in that narrow corridor between Saturn's cloud tops and the inner edge of the D-ring, 1,200 miles of space that looked, on paper, like nothing much, but space that had never been sampled, never been measured from the inside, never been trusted. And Cassini was not a small craft. It was a machine the size of a school bus, carrying instruments worth more than most countries' space programs. And if the gap turned out to be threaded with debris, sharp, fast-moving ring particles too small to see from a distance, but large enough to shred a solar panel or crack a sensor, then the whole finale would end not in science, but in silence. So they pointed the high-gain antenna forward. The great dish built by the Italian Space Agency, the one that had been sending data across 1 billion miles for 20 years, became a shield. If something was going to hit Cassini on that first pass, it was going to hit the antenna first. And Cassini dove. And the gap was nearly empty. Quieter than expected. Quieter, in some ways, than the space outside the rings. A vast, clean corridor with almost nothing in it, which was its own kind of surprise and its own kind of gift. Because empty meant they could use it. 22 times, so that is what they did. It's what? Each orbit brought Cassini skimming through that gap, lower than anything had ever flown near Saturn, close enough to the cloud tops that the planet's gravity became something you could feel in the numbers coming back through the signal. And that feeling, that gravitational pull recorded in the Doppler shift of Cassini's radio transmissions, was exactly what the scientists needed. Because gravity is mass, And if you can measure the gravitational signature of the rings separately from the gravitational signature of the planet, you can weigh the rings. For the first time in history, someone was weighing Saturn's rings. The answer, when it came, was astonishing in the most quiet way, not a roar, a whisper. The rings, all of them, the A ring, the B ring, the C ring, the D ring, that luminous sweep of ice and shadow stretching millions of miles, all of it together weighed roughly 4/10 of the mass of Mimas. Mimas, which is itself a modest little moon about 400 kilometers across. You could fit hundreds of Mimases inside Earth. And Saturn's rings, which look from here like the grandest, most permanent structure in the solar system, the signature feature of a planet you can see with your naked eye, contain less material than less than half of that small, unremarkable moon. That is a small number, a surprisingly, almost shockingly small number, and a small number has consequences. Here is the logic, and it arrives gently, one step at a time. The rings are made almost entirely of water ice, roughly 95% ice by mass, and they are bright, extraordinarily bright. When you look at Saturn through a telescope and the rings catch the sunlight, what you are seeing is the reflected glare of billions of tons of clean, white ice, almost as reflective as fresh snow. And that cleanliness is not a coincidence. It is a clock. Space is not empty, not truly. There is a constant slow rain of material falling through the solar system, dark, carbon-rich dust from micrometeorites, ancient and sooty, drifting in from comets and asteroids that broke apart long ago. This material falls on everything. It falls on the moon, which is why the moon's surface is covered in dark grey regolith rather than gleaming rock. It falls on ring systems too, and if Saturn's rings had been sitting in place for 4.5 billion years, the age of Saturn itself, they would be grey, dark, dirty with accumulated cosmic soot, the same way an old snowbank on a city street turns grey and then black as the days pass. But they are not grey, they are white, almost pristinely so, which means they have not been collecting that soot for very long. Combine the cleanliness with the measured mass, which is too low to have diluted billions of years of incoming pollution, and you arrive at a number that the Cassini team published in 2019 in a paper led by Luciano Yes and colleagues in the journal Sciences. The rings of Saturn are not ancient. They are roughly 100 million years old, perhaps a few hundred million at the outer edge of the estimate, but almost certainly not more than that, and possibly less. Some analyses suggest the rings could be as young as 10 million years. Let that land for a moment, while you rest where you are. 100 million years ago, give or take, the dinosaurs had not yet disappeared. They were still here, still walking, still filling the Cretaceous sky with their noise and their weight. And at that same moment, or possibly even after that moment, Saturn had no rings. Not these rings. Just a planet tilted slightly on its axis, circling the sun, ringed perhaps by nothing more than scattered debris. The great rings of Saturn, the ones that have been in every astronomy textbook, every childhood picture of the outer solar system, every image of the night sky that made you feel small and awed and alive. Those rings may be younger than the dinosaurs' extinction. This is not a minor revision to what we thought. This is a fundamental rewrite, and there is more. Because the rings are not merely young, the rings are dying. This is where planetary protection and deep space science arrive at the same destination from two different roads. Cassini was sent into that gap partly to protect Enceladus and Titan from contamination. But inside that gap, its instruments were sampling what was actually there. And what was there, falling inward along the magnetic field lines into Saturn's upper atmosphere, was ring material. Water, yes, but also methane, ammonia, carbon monoxide, molecular nitrogen, complex organic molecules, silicate-bearing nanograins. The rings were not simply sitting in place above the planet, they were dissolving into it. Slowly but measurably, the rings were raining down into Saturn. The phenomenon even has a name: ring rain. It had been suspected since the Voyager spacecraft flew past Saturn in the early 1980s and noticed strange dark banding in Saturn's upper atmosphere, a subtle chemical signature that scientists of that era hypothesized might be caused by material falling in from the rings. That was a 30-year-old guess. Cassini converted it into a measurement. The measured rate is staggering in its implications, if not immediately in its scale. Depending on the method and the region of the ring system, estimates range from hundreds to as many as 10,000 kilograms per second pouring from the rings into Saturn's atmosphere. Per second. Every second, continuously, the rings are losing mass, pouring themselves downward, mixing with the planet below, dissolving into something neither ring nor atmosphere, but both and neither. And if you take that rate of loss and hold it against the total measured mass of the rings, you arrive at a remaining lifespan, a deadline. The rings, at current rates, have somewhere between 100 and 300 million years left. After that, they will be gone, drained, absorbed. Saturn will still be there, enormous and golden and cloud-banded, but the rings will be gone. And whatever comes after us, whatever looks up from this planet or another and points a telescope at the sixth planet from the sun, will see a different sky. We exist in the window. That is what Cassini showed us. The billions of years on either side of this moment are ringless Saturn, unremarkable, just another gas giant. But right now, in this narrow corridor of geological time, in this specific 10-minute sliver of cosmic history that happens to contain us and our telescopes and our spacecraft and our wondering, Saturn has rings. Which raises, of course, the quiet question of where they came from. If they are not primordial, if they did not form with Saturn 4.5 billion years ago, then something made them. Something relatively recent. The leading explanation is a moon, or perhaps a comet, that wandered too close and crossed what astronomers call the Roche limit. The Roche limit is the invisible boundary around any massive body inside of which tidal forces become stronger than the gravitational cohesion holding a smaller object together. Cross that line and the object does not simply fall, it is pulled apart, stretched, disaggregated. A moon that crosses the Roche limit around Saturn does not become a crater or an impact scar, it becomes a ring, clean, bright, cold, water ice wreckage, spread across the plane of Saturn's equator, precisely what we see. The debate is still open. A shredded moon is the favored model, but a particularly large comet is not ruled out, and the specific details of the event remain unknown, the culprit unnamed, the moment unwitnessed. What Cassini gave us is not a complete answer. It gave us the constraint. The rings are young, that means they came from somewhere recently, and whatever that something was, it was destroyed inside the Roche limit, probably not long before the first hominid stood upright on a warm African plain and looked up at the sky without yet having a word for what they saw. The Outer Space Treaty of 1967, in its Article 9, commits the nations that signed it to avoiding the harmful contamination of celestial bodies. From that treaty came the framework administered by the Committee on Space Research, COSPAR, which assigns planetary protection categories to every mission, every target, every trajectory. The categories range from simple tracking requirements all the way to the strictest protocols for missions targeting potentially habitable environments. Enceladus and Titan, after what Cassini found, sit near the top of that spectrum, and Cassini, carrying 3 radioisotope thermoelectric generators running on plutonium-238, could not be left to drift. Not with Enceladus below and its ocean intact. not with Titan and its methane seas waiting in the haze. A spacecraft carrying earthly microorganisms that might have survived in dormancy through 20 years of cold and radiation, could not be allowed to arrive on those surfaces uncontrolled. The COSPAR categories demanded certainty. The only certainty available was Saturn's atmosphere, which would accomplish what the name implies: full incineration. Nothing survives. The moon Cassini died to protect is the one it found itself. That is the self-fulfilling shape of it. In 2005, Cassini's instruments detected water vapor and ice particles erupting from fractures in the southern pole of Enceladus. Fractures that geologists came to call the tiger stripes, 4 long parallel lines cutting across the surface through which the moon breathes ocean into space. The plume rising from those stripes was later found in work led by J. Hunter Waite and his colleagues and published in Science in 2017 to contain molecular hydrogen. H2 and molecular hydrogen at those temperatures and pressures rising from an icy moon means something specific. It means water reacting with rock at high temperature on the ocean floor. It means hydrothermal vents. It means the same basic chemistry that, on Earth, supports entire ecosystems in total darkness at the bottom of the sea. Cassini did not find life on Enceladus. That word must be said plainly and held carefully. What it found were ingredients, water, organic molecules, a chemical energy source. The conditions that on the one world we know of where life arose were present at the beginning. Whether those same ingredients in that dark sub-ice ocean have assembled into something that metabolizes or replicates or responds, that is a question Cassini could not answer. That is a question that requires going back, but it is the question that made Enceladus untouchable. And so it is the question that killed Cassini. Saturn's rings, meanwhile, are still reigning. Right now, as you lie there, wherever you are, with whatever soft light is still on, and whatever sound is still moving through the room, 10,000 kilograms of ice and organic molecules may be falling from those rings into Saturn's cloud tops every second. Silently, continuously, without drama. The gap is empty, the plumes are rising, the rings are younger than we imagined and older than they will be. And here is where the story shifts. Not away from Enceladus, not away from those plumes still rising invisibly in your imagination, but toward the decision those plumes forced, toward the machine itself, toward what happened in the spring and summer and early autumn of 2017 in the space between a planet and its rings where no spacecraft had ever been. Because the grand finale wasn't just an ending, it was a specific shape of ending, a shape that mattered. Let's take it slowly. By early 2017, Cassini had been orbiting Saturn for nearly 13 years. 13 years is a long time for a spacecraft. It had arrived in July of 2004, firing its main engine for 96 minutes to slow itself just enough for Saturn's gravity to catch it. A maneuver where if the engine had failed, the craft would have sailed past and been lost forever, and there would have been nothing anyone could do, but the engine didn't fail. It caught. And for the years that followed, Cassini moved through the Saturnian system like a visitor who had decided to stay, looping outward to the moons and back in toward the planet, building a map of everything in between. 453,000 images, dozens of moon flybys. The Huygens probe released in December 2004 and landed on Titan's surface on January 14, 2005, the first landing in the outer solar system ever. Data returned across 4.9 billion miles of empty space, a distance so large that the radio signal traveling at the speed of light took more than an hour to cross it. And then, in those final months, the fuel ran low. Not out, low. There was still propellant in the tanks. Still enough for the grand finale itself. But the margin was shrinking, and without propellant, Cassini could not orient its thrusters, could not keep its antenna pointed at Earth, could not maintain the precise attitude control that kept it a functioning spacecraft rather than a slowly tumbling piece of metal. And once the fuel was gone, truly gone, the craft would drift, uncontrolled, in a system that now included an ocean with the possible ingredients for life. That was the thing that could not be allowed. So the engineers at JPL, the mission planners, the planetary protection specialists, they made the decision that had been written into the mission design years earlier, long before Enceladus had revealed what it was. Cassini would be flown deliberately into Saturn's atmosphere. Not crashed, not dropped, flown, with intention, with precision, on a trajectory that had been calculated carefully that used the last of its propellant to keep the antenna pointed at Earth even as it entered the clouds, so that it could keep transmitting right up to the moment the signal was lost. The date was set, September 15, 2017, but before that date, there were 22 dives. 22 dives through a gap between Saturn's cloud tops and the inner edge of its D-ring, the innermost, faintest, most delicate of the main ring structures, a region approximately 1,200 miles wide, roughly 2,000 kilometers, that no spacecraft had ever entered, that no one had ever seen up close. That existed in the mission planning as a kind of white space, a region skipped because the risk was too uncertain. For most of Cassini's orbital life, it stayed well outside the rings, far safer there, far less likely to encounter particles at high relative velocity that could damage instruments or compromise navigation. The rings are not solid, remember. They are a vast, dispersed collection of individual pieces of ice and rock, ranging in size from grains of dust to chunks the size of houses. Flying through them is not flying through a wall, but it is flying through a field of debris at thousands of kilometers per hour, and a single piece of material at the wrong size and the wrong angle can do catastrophic things to a spacecraft. So they had kept Cassini out, until they had no reason left to be cautious. Because here is the thing, that gap between the planet's upper atmosphere and the bottom of the rings had never been sampled, never been measured. And from outside the rings, from the safe, distant orbits Cassini had spent years in, there were certain things that simply could not be determined. The mass of the rings was one of them. To weigh something from a distance, you need to know how its gravity pulls on something nearby. But from outside the rings, Saturn's own gravity dominated everything. The rings' contribution was buried in that signal, too small to separate out. To hear the rings' gravitational whisper, you had to move close enough that Saturn's roar fell into the background, or rather, could be distinguished from it. You had to fly between them, between the planet and its rings. And so they did. The first dive was April 26, 2017, and in the days before that first plunge, there was real uncertainty about what they would find. The gap between the cloud tops and the D-ring was estimated to be relatively empty of large particles. Models suggested the region should be clear enough to pass through safely, but models are not measurements. They had never flown there. They simply did not know. So for that first pass, they did something practical. They turned the spacecraft around and pointed the high-gain antenna, the large, dish-shaped radio antenna, roughly 4 meters across, built by the Italian Space Agency, the same dish that had been Cassini's primary link to Earth for 2 decades. They pointed it forward, like a shield, like someone walking into a sandstorm with their jacket over their face. If there were particles in that gap, they would hit the antenna first instead of the instruments. The antenna could survive impacts the sensors could not. It was a hedge, a reasonable precaution for an unknown environment. The dive lasted several hours. The signal was interrupted during the closest approach when the antenna was facing the wrong direction to transmit, and the team at JPL waited and then the signal came back. Cassini had made it through. And the gap, that 200-mile corridor between a planet and its rings, was nearly empty. Remarkably empty. The team called it, with the slightly tired humor of people who have been running on adrenaline and coffee for weeks, the big empty. The hazard they had braced for, the reason they had used the antenna as a shield, was not there, or not there in the quantities they had feared. From that point on, the passes continued without the antenna shield. The craft oriented normally, instruments pointing outward, sampling the environment at each closest approach. 21 more times it dove through that gap, 21 more chances to measure something no one had measured before. And here is what the gap gave them. During each proximal orbit, as Cassini swept through its lowest point and closest approach to Saturn, mission scientists tracked the spacecraft's position with extraordinary precision, not by radar or by camera, but by radio. The Doppler effect, the same principle that makes an ambulance siren rise in pitch as it approaches you and fall as it recedes, the same principle, applied to the radio signal Cassini was beaming back to Earth, allowed the team to measure tiny changes in the spacecraft's velocity as it moved through the Saturnian system. Tiny changes, changes in speed on the order of fractions of a millimeter per second, because gravity pulls. Everything with mass pulls on everything else with mass, and the more massive the object, the stronger the pull, and the closer you are, the stronger the pull still. And as Cassini flew between Saturn and its rings, it was being pulled by both of them simultaneously, pulled downward by Saturn's enormous gravity, pulled sideways and upward, slightly, by the rings above it. The rings pulled on Cassini, and because they pulled on it, they changed its speed. A tiny change, but measurable. This is how you weigh a ring system from the inside. You fly a precisely calibrated spacecraft through the gap, you track its motion with extraordinary care, and you disentangle the gravitational contribution of the rings from the gravitational contribution of the planet below. It is painstaking work. It requires modeling Saturn's own gravity field in detail, accounting for its oblateness. Saturn is notably squashed at the poles and bulged at the equator, accounting for the gravitational pull of each major moon in the system, and then extracting from what remains the signature of the rings themselves. Lucas and his colleagues published the result in the journal Science in 2019. The number they found after all of that careful work was this: the total mass of Saturn's entire ring system, all of the A ring and the B ring and the C ring and the fainter D and F and G and E rings, every bit of ice and rock spread across hundreds of thousands of kilometers of space. The rings you can see with a backyard telescope on a clear night from your own backyard. All of it together weighs approximately 1.5 times 10 to the 19th kilograms. That is a large number in the abstract. It is 15 quintillion kilograms. It is more mass than exists in most things you will ever think about. But in the context of what it is, a planetary ring system, a structure that spans a distance greater than the diameter of Jupiter, it is shockingly small. Here is a way to hold it. Saturn has a moon called Mimas. You may have seen photographs. It looks uncannily like the Death Star from a certain famous science fiction film because it has a large impact crater on one face that gives it an eerie geometric symmetry. Mimas is not a large moon. It is roughly 400 kilometers across, a lumpy sphere of ice and rock that orbits Saturn in the inner part of the system. Compared to our own moon, it is tiny. Compared to most things you can see in the sky, it is inconsequential. The entire mass of Saturn's rings is roughly 0.4 times the mass of Mimas, less than half of a small moon. All of those rings are to millions of kilometers of them, the most visually spectacular structure in the solar system, the feature that has defined Saturn in every human mind that has ever pointed a telescope at the sky, less than half the mass of an object 400 kilometers across. That number changed everything, because of what it implies about time. Saturn is old. The planet itself formed roughly 4.5 billion years ago, in the early period of the solar system when gas and dust and ice were coalescing under gravity into the planets we know. For most of the time since Galileo first turned his crude telescope toward that wandering bright star in 1610 and noticed, with confusion, that it seemed to have companions, he described it as having ears, as appearing almost triple-bodied, because his optics could not resolve what he was seeing. For most of the time since then, astronomers had assumed that the rings were just as old as the planet. 4.5 billion years, primordial, formed in the same early chaos that made the moons, left behind when the solar system was young, persisting unchanged through all the intervening eons. Christian Huygens in 1655 correctly identified that what surrounded Saturn was a ring, a flat, detached disk extending out from the planet. He did not know what it was made of or where it came from, but he saw its shape clearly enough. And in the centuries that followed, that ring became simply part of Saturn, the way Saturn's storms are part of Saturn, the way its many moons are part of it. Ancient, given, permanent. The mass measurement said otherwise. Here is the logic, and it is worth sitting with because it is the heart of the discovery. Outer space is not empty. This is easy to forget, lying in the quiet of wherever you are, because our everyday experience of the night sky is of darkness and stillness. But the solar system is full of traveling debris, comets, asteroids, the constant microscopic rain of micrometeoroids, tiny particles of rock and carbon, and organic material drifting through interplanetary space. And some of that rain falls onto everything in its path, including rings. When a dark, carbon-rich micrometeoroid hits a ring particle, a piece of ice, it doesn't pass through, it embeds, it coats. Over time, a surface that was once clean, white ice becomes contaminated with dark material, the way a snowfield in a city gradually turns grey, and then black as soot and grit accumulate in it. Ice is reflective. Dark carbon compounds are not. And so a ring that has been collecting micrometeoroid pollution for a very long time will be darker than a ring that has been collecting it for a short time. Saturn's rings are extraordinarily bright, extraordinarily clean, roughly 95% pure water ice by mass, the rest being rocky and organic contaminants. If you look at photographs of the rings from Cassini, and they are worth looking at when you are not trying to sleep, they are white and pale and almost luminous, catching sunlight and scattering it beautifully in all directions. That cleanliness is a clock, and that clock is running. If the rings were 4.5 billion years old, they would have been collecting micrometeoroid contamination for 4.5 billion years. They would not look like this. They would be dark, grimy, dull. Not the pristine, icy structures that Cassini photographed and measured. Their cleanliness is inconsistent with immense age. It points to youth. Now combine that with the mass. A low-mass ring cleans up faster than a high-mass ring. There is less material to dilute the incoming dark particles, so the contamination signal shows up sooner. The small mass makes the cleanliness argument even stronger. Less mass, faster darkening, and yet the rings are still almost pure white. Put those two constraints together, low mass and high cleanliness, and the leading interpretation, shared by a large body of researchers who have worked through the Cassini data carefully, is that the rings are not 4.5 billion years old. They are somewhere between roughly 100 million and a few hundred million years old, perhaps as young as 10 to 100 million years in some estimates. Some researchers argue for a somewhat older age, closer to the higher end of that range, and the debate is not entirely closed. But the consensus that has emerged from the grand finale data tilts strongly toward youth. The old assumption of primordial rings has not survived the measurement. 100 million years ago on Earth, dinosaurs were in the middle of their reign, the Cretaceous period. Flowering plants were just beginning to spread across the continents. The continents themselves were in arrangements nothing like today's maps. And Saturn, in this picture, did not yet have the rings we see now. Or if it had something earlier, what we see now was not there. The vast, iconic, unmistakable ring system that defines the planet in every human imagination, post-Galileo, may be a relatively recent arrival. The rings may be younger than the flowering plants. That is not a poetic exaggeration. It is where the data, carefully and honestly read, points. And here is the thing that gives the grand finale its peculiar, recursive significance. If Cassini had followed a conventional end-of-mission trajectory, had been disposed of differently, had been sent into an orbit that would keep it away from the inner planets but did not bring it between Saturn and its rings, none of this would be known. The trajectory that killed Cassini was also the only trajectory from which the rings could be weighed. The same maneuver, the same pass, the same set of 22 dives through the big empty. The death was the experiment. You cannot separate them, no matter how you try. The planetary protection requirement forced a trajectory. The trajectory demanded the gap. The gap, threaded 22 times, gave the Doppler signal that weighed the rings. The rings, once weighed and combined with their measured cleanliness, gave an age. And the age overturned an assumption that had stood for 4 centuries. If the spacecraft had lived, if there had been more fuel, if Enceladus had turned out to be barren, if the planetary protection calculus had come out differently, it would have been disposed of in some other way. And we would still today be assuming that Saturn's rings are primordial, ancient, given, as old as the planet itself. It is strange to think about. A decision made to protect possible life on a small icy moon. A decision that required threading a spacecraft through a gap nobody had ever entered. A decision that happened to place sensors in exactly the right location to answer a question that nobody had previously had the data to answer. The ethics of planetary protection and the science of ring chronology linked by nothing except the specific shape of one spacecraft's final months. Let's stay with the mass measurement for a moment more, because there is something in it that is easy to glide past. 1.5 times 10 to the 19th kilograms, less than half the mass of Mimas. You can put that another way. If you took all of Saturn's rings and gathered up every particle of ice and rock from across those hundreds of thousands of kilometers and compacted them together into a single object, you would get something smaller than Mimas, something roughly 400 kilometers across at most, and quite possibly smaller since Mimas is already not entirely ice. You would get an object that, sitting alone in space without a planet next to it, you might easily overlook. That is what the rings are. Dispersed, they look vast and permanent and magnificent. Concentrated, they are less than half a small moon, and the reason they look vast is that they are spread thin, extraordinarily thin. The rings of Saturn extend outward for hundreds of thousands of kilometers from the planet's equator, but they are on average perhaps 10 meters thick, perhaps less in some regions. 10 meters, the width of a modest living room, a structure that would take light more than a second to cross from inner edge to outer edge, and yet you could stand in it and it would barely reach the second floor. That thinness is part of why they look so spectacular from the right angle. They catch sunlight across an enormous area. It is also part of why, once you know their mass, the math resolves into something startling. Because that thin, spread out, low mass, remarkably clean ring system is right now being lost. Right now, continuously. At rates that, measured from the inside for the first time by Cassini's instruments during those 22 dives, tell a story about time that is different from what anyone expected. But we should come to that gently. The measurement of the rain deserves its own space, its own slow walk through what the instruments found falling between the rings and the planet below. And there is also, before we get there, the story of how those 22 dives ended. How the last one was not a dive at all, but a one-way descent. Let's back up slightly to April 22nd, 2017, 4 days before the first grand finale dive. There was one more encounter with Titan. Titan had been Cassini's gravitational companion for the entirety of its time at Saturn. The moon was massive enough and perfectly placed enough in its orbit that mission planners could use flybys of Titan the way a juggler uses their hands, to toss Cassini from one orbital configuration to another, adjusting the shape and orientation of the spacecraft's path around Saturn without burning precious fuel. Over the 13 years of the mission, Titan gravity assists redirected Cassini dozens of times. They are the reason the mission was able to visit so many different moons and ring regions with the limited propellant it carried. Titan helped launch the mission, in a sense. After its 2004 arrival at Saturn, Cassini used Titan repeatedly to shape its orbit, and at the end, Titan closed the circle. The encounter on April 22nd was a relatively distant one, a final gravitational nudge. Engineers and mission planners referred to it with a certain quiet affection as the goodbye kiss. What it did was bend Cassini's orbit just enough that the lowest point, the periapsis, the closest approach to Saturn, dropped below the level of the D-ring's inner edge, into the gap, permanently. Before that flyby, the orbit was set up so that Cassini's closest approach was still outside the rings, still in the safe, familiar territory it had inhabited for years. After the flyby, it was inside. Every subsequent orbit would bring it through the gap. And there were 22 of them planned, each one trimmed slightly closer, slightly deeper, until the final one on September 15th was not a dive through the gap at all, but a plunge directly into Saturn's upper atmosphere. The moon that Cassini was being destroyed to protect, Titan, one of the two primary contamination concerns alongside Enceladus, was also the moon that delivered the killing blow. The moon launched it, and the moon aimed it. There is something in that which resists clean description, a kind of astronomical irony so complete it feels engineered, though of course it wasn't. It was just orbital mechanics following laws that don't know anything about poetry or narrative or the feelings of people watching telemetry in a room in Pasadena, but it is the shape the facts have taken. And so Cassini dove. April 26, 2017, the antenna forward. The team in mission control watching data they couldn't quite predict. The first pass through the big empty, tense and quiet, and ultimately uneventful. The craft surviving, orienting, transmitting, looping back out on its elliptical path, and then falling inward again, and again, and again. 22 times through a gap nobody had mapped, sampling what was there, measuring what moved, recording what fell. The mass of the rings emerged slowly, orbit by orbit, as the Doppler data accumulated and the scientists began the painstaking work of separating what was Saturn from what was rings, from what was spacecraft dynamics, from what was everything else. It is not the kind of measurement you read off a dial. It is the kind of measurement you compute carefully over months, checking and rechecking the models, looking for systematic errors, consulting colleagues, revising. What Luca IS and the team published in 2019 was the product of all of that accumulated care. And when the number settled, it settled at roughly 0.4 times the mass of Mimas. Small. Surprisingly, uncomfortably small. Small enough that the age argument could not be avoided, because the cleanliness of the rings had always been a little mysterious. Even before the grand finale, astronomers had noted that Saturn's rings were brighter than you'd expect them to be if they were truly ancient. But without a firm mass measurement, the argument was incomplete. You could invoke various mechanisms. The rings could be continuously refreshed by new material from the moons, a kind of ongoing resupply that kept them clean despite their age. You could argue that the contamination models were uncertain. You could gesture at the complexity of the system and say that perhaps things were not so simple. Once you had the mass, you couldn't gesture anymore. The mass closed the argument. A low-mass ring cannot sustain a resupply scenario at the scale needed to keep it clean across 4.5 billion years. There simply isn't enough material to absorb 4.5 billion years of micrometeoroid contamination and still emerge looking the way they do. The numbers don't balance, so the rings are young. And this is a sentence that, if you hold it long enough, begins to feel genuinely strange. And because we have known about Saturn's rings since 1655, humanity has studied them, sketched them, photographed them, sung about them, used them as visual shorthand for the idea of a planet. They are perhaps the most recognizable planetary feature in the entire solar system. And they are young. Younger than the Himalayas, younger than the dinosaurs' extinction, younger, possibly, than the first flowering of plants on Earth. We have always seen Saturn's rings as something ancient and permanent, something you could measure as a given constant of the universe, the way you measure the speed of light or the mass of a proton, something that was there before us and would be there long after. The grand finale said, "Not quite." It said, "You arrived in time. This is a coincidence, your species being here when the rings are still here. A cosmic coincidence, the kind that doesn't feel meaningful when you trace it back to its causes, just orbital mechanics and orbital debris and the specific timing of whatever event created the rings in the first place. But the kind that feels meaningful in the quiet, lying somewhere soft, listening to a voice tell you that the rings of Saturn are young and bright and burning away. Because they are burning away. The measurement of the mass was one discovery, the measurement of the rain was the other. And the rain is where the dying lives, in the slow, steady 100-million-year drain of ice and molecules from the rings into the planet below. That story is being written in Cassini's data even now, in the years since the spacecraft went silent. But it would be wrong to rush to it before letting the mass measurement breathe for a moment longer, because it is, in its own right, one of the most fundamental things the mission returned, not the most visually dramatic. The photographs of ring structures, the images of Enceladus's plumes, the views of Titan's surface through Huygens's cameras, those are the images that will persist in textbooks. But the mass is the foundation on which the age argument rests. It is the bone of the thing, and it was recoverable only from inside, only from the gap, only from the trajectory that destroyed the spacecraft. The death was the experiment. That is not metaphor, that is mechanism. 22 times through the big empty, listening to a spacecraft's own velocity change under the gentle tug of ice spread across hundreds of thousands of kilometers of space, and from that signal extracting a mass, and from that mass extracting an age, and from that age overturning 4 centuries of assumption. That is what happened in the gap between a planet and its rings between April and September of 2017. That is what the goodbye kiss set in motion. And there is still the rain to discuss. Still the question of where the rings are going and how fast, and what Cassini found in the act of falling through what was falling. But let the rings be young for a moment longer. Let that fact settle somewhere in the mind, the way facts sometimes do when they are strange enough, not as a piece of information to be filed and moved on from, but as a small rearrangement of how things feel. Saturn with rings is not the given. Saturn with rings is the lucky moment, and the moment was measured. So let's talk about the rain, because while Cassini was threading those 22 orbits through the big empty, it wasn't only listening to its own weight change in the gravitational pull of a planet and its rings. It was also catching things, actual physical things, molecules, grains, material that had been part of the rings and was now falling, drifting down along magnetic field lines and arcing into Saturn's upper atmosphere. And the instruments were ready for it. The magnetospheric imaging instrument and the ion and neutral mass spectrometer, the INMS, were designed, among other purposes, exactly for this: to taste the local environment, to identify what was present in the space the spacecraft was moving through. And during the grand finale, that space was not empty, not of particles dangerous to the spacecraft. That much we have already settled, the big empty, but not empty of chemistry either, not empty of the fine, constant, almost imperceptible drift of material raining down from the rings into the world below. The word rain is the one researchers used, ring rain, and it is the right word even if you have to hold it loosely, because it is not rain in the way you might picture it on a warm evening, water on a window, puddles forming. It is more diffuse than that, more spread across an entire planet's worth of atmosphere, more ghost-like. But it is real. It has been measured. It was measured by Cassini while Cassini was still alive, falling through the outermost layer of Saturn's skies in the last months of its life. Here is what the instruments found. The material coming down is not simply water ice. You might expect that, given that the rings are roughly 95% water ice by mass. You might expect that what falls from them would be clean water, more or less, a trickle of ice grains and vapor drifting planetward. But it is not that simple. It is not that clean. What Cassini detected raining into Saturn's atmosphere was a cocktail. Water, yes, but also methane, ammonia, carbon monoxide, molecular nitrogen, and then something even more interesting, organic and silicate-bearing nanograins, tiny particles of complex chemistry, tiny particles that, in one sense, have no obvious business being in a ring made mostly of water ice, and yet there they were. The work was led in part by Hunter Waite and his colleagues, the same group that had found molecular hydrogen in Enceladus's plume the year before. Published in Science in 2018, the paper laid out what Cassini had sampled during those close passes, and the answer was not a simple stream of meltwater. The rings were not just losing mass, they were losing chemistry. Complex, varied, organics-laden chemistry pouring into the upper atmosphere of a gas giant at a rate that, when you stand back from it and look at the numbers, is genuinely startling. Let's take a moment with those numbers because they matter. The measured infall rate, depending on the method and the data set, ranges from somewhere in the hundreds of kilograms per second up to approximately 10,000 kilograms per second on the higher estimates. The figure associated with the work of James O'Donoghue and his colleagues, published in Icarus in 2019, sits toward the higher end of that range. 10,000 kilograms per second is the number that tends to get used as the headline, and it is the honest headline, though it is worth knowing the range is real and the methods differ, not hundreds, not a symbolic trickle, thousands of kilograms of ring material every second disappearing into the planet below. 10,000 kilograms per second. Try to make that feel like something for a moment. In the time it takes to read a single sentence, Saturn has absorbed tens of thousands of kilograms of what used to be its rings. Quietly, invisibly to any eye we could point at it from Earth. But measured, confirmed, quantified by a spacecraft in the last months of its life, threading orbits through the narrow band between a planet and a ring, doing science until the moment it could no longer hold course. And what does that number mean for the rings themselves? This is where the age and the death converge. because once you have the mass, that 1.5 times 10 to the 19th kilograms, that 0.4 Mimas, that shockingly small sum we recovered from the Doppler data. And once you have the drain rate, the math is not complicated in concept, even if the specifics carry uncertainty. You are asking how long until the balance tips to zero? How long until the rings have given themselves away entirely? The answer, at the rates Cassini measured, is something on the order of 100 to 300 million years. Some estimates compress toward the lower end, 100 million years. Others allow for somewhat longer. But the range is geologically short in a way that the phrase 100 million years can obscure if you say it quickly and move on. Let's not move on quickly. The solar system is 4.5 billion years old. 100 million years is roughly 2% of that. The rings of Saturn, the most visually iconic structure in this solar system, the feature that makes Saturn immediately recognizable to anyone who has ever glanced at a photograph, the thing that made Galileo think he was seeing a triple body in 1610, those rings, at the rates we measured, have perhaps 100 to 300 million years left. And if they are also only 100 million years old in the first place, which the mass and the cleanliness suggest is possible as the leading interpretation, then we are living in a fleeting window. A window that opened roughly when the last dinosaurs were alive, or perhaps more recently still, and that will close on a timescale that is long by human reckoning but short, remarkably short, by planetary reckoning. We are the lucky ones, not in the sense of having done anything to earn it. In the pure sense of having happened to exist at the right moment, right now, in the period when Saturn has rings. There is something worth pausing on here before moving forward, because the idea of the rings being temporary is not simply a data point about Saturn, it is a quiet philosophical adjustment to how we think about what we are seeing when we look up. The solar system we observe is not a finished, static thing. It is a process. Things form, things age, things lose mass and fall into planets and disappear. What looks permanent from a human vantage point, because it has been there for all of recorded history, because Galileo saw it, because every telescope pointed at Saturn has seen it, is still, by the standards of the universe, ephemeral. The rings were not always there. They will not always be there. We caught them in the middle. And Cassini, by dying in the way it had to die, told us so. Now, there is something else the Voyager spacecraft noticed back in the early 1980s when those two probes flew past Saturn, and everything changed in terms of what we could resolve from a distance. Voyager's scientists studying Saturn's upper atmosphere noticed something odd. Dark bands in certain latitudes, narrow, unexpected darkening in a pattern that didn't have an obvious explanation in the cloud chemistry alone. A hypothesis was floated: ring rain. Maybe the rings were depositing material along magnetic field lines that connected to the planet, and that material was altering the atmosphere slightly where it arrived, creating those dark features. It was a good hypothesis. Plausible. Consistent with what was known about Saturn's magnetic field structure. But it was a hypothesis. A hunch built from unexpected observations, held at arm's length for lack of the means to confirm it. That was 1980 or 1981, 30-odd years past. Cassini converted that 30-year hypothesis into a measured, quantified, in situ confirmed fact. Not just material might be falling from the rings, but here is what the material is, here is what it contains, here is roughly how fast it is arriving, here is the chemical signature of it in Saturn's own atmosphere. A hypothesis from the Reagan era became a quantified death sentence, courtesy of a spacecraft built in the 1990s that spent its last months threading orbits through the unexplored gap and tasting what was falling through it. That is a 30-year story of patient science, and it ended with a mass spectrometer sampling actual molecules in the actual ring rain while the spacecraft that carried it was using up the last of its fuel. There is something quietly beautiful about that sequence if you let yourself feel it. But the rings and the rain are not all the grand finale returned. Let's take a turn towards something that might be even stranger, because the same 22 orbits that gave us the ring mass and confirmed the ring rain did something else that is easy to overlook in the headlines about the rings dying and the age being wrong. They gave us something from inside the planet. Saturn's rings, it turns out, are not just rings. They are also a recording instrument. This is the part that might sound most like science fiction and least like hard data, but it is the hard data, and it has a name: chronoseismology, ring seismology. It is, in concept, directly analogous to the way that geologists on Earth study our planet's interior by measuring how seismic waves travel through it. When an earthquake happens, the waves ripple outward and inward, and where they slow down or speed up or reflect tells you something about what they passed through. The density and composition of the layers beneath your feet. The interior of the Earth is not directly visible, but the waves that pass through it carry the signature of what they encountered. Saturn vibrates. All large planets do in their own way. Saturn has internal oscillations, normal modes of vibration, the way a bell rings at certain frequencies and not others, shaped by the planet's own mass and density distribution. And those vibrations, propagating outward through the planet, reach the rings, they disturb the rings, they create structures in the ring material, waves, spirals, density patterns, that are, if you know how to read them, a record of what is happening inside. The C-ring, Saturn's innermost major ring band, turned out to be a particularly good seismometer. Matthew Hedman and Philip Nicholson were among the researchers who recognized these structures for what they were. And what they were was a transcript, density waves in the C-ring encoding the frequencies of Saturn's internal oscillations, a ring that is, in some sense, listening to the planet it orbits. Christopher Mankiewicz and Jim Fuller took this further, building on the Cassini ring data, and published in 2021 results that pointed towards something unexpected about Saturn's interior. The planet likely does not have a sharp, compact, rocky core at its center, the way simpler models had assumed. Instead, it appears to have what they called a diffuse or fuzzy core, a region that occupies a significant fraction of the planet's radius, where rock and ice and gas are intermixed, smeared and blended rather than neatly layered. Not a hard stone at the center of a gas balloon. Something more ambiguous, something more mixed. This is the kind of result that planetary scientists will be working to understand for years. The interior of a gas giant is not an easy place to theorize about. The pressures are unlike anything you can replicate in a laboratory, and the material behaviors are genuinely strange. But having a measurement, having a constraint from the rings themselves, from the way vibrations propagate through a planet and register in the structures of its ice, is a different category of knowledge from a model with no anchor. The rings recorded it. Cassini read the recording. Mankiewicz and Fuller did the interpretation. And Saturn's fuzzy core is the result, all from the same 22 orbits, all from the same trajectory that weighed the rings and sampled the rain. The act of dying inside the rings yielded everything, and there is one more puzzle the grand finale deepened without fully solving. One that is, in its way, quietly maddening: Saturn's magnetic field. Every planet with an active interior generates a magnetic field. Earth's is tilted roughly 11 degrees away from its rotational axis. That is why a compass needle doesn't point exactly to the geographic North Pole. Jupiter's field is also tilted. Neptune's, Uranus's, dramatically so. This tilt is, in fact, expected. The dynamo theory that describes how magnetic fields are generated in the conducting fluid interiors of planets suggests that a perfectly symmetric, perfectly aligned field, a field with zero tilt, is unstable. It should not be maintainable over geological time. It should drift, tilt, wander. Saturn's magnetic field has a tilt of less than 0.06 degrees, less than 1/10 of a degree, essentially perfect alignment with the rotational axis, a field so symmetrical that it challenges the theory meant to explain it. This is not a minor curiosity. This is a genuine open problem. Dynamo models that work for Earth and Jupiter simply do not comfortably accommodate a field this symmetric. Something in Saturn's interior is maintaining a near-perfect alignment that the physics says should not be stable. What that something is remains unresolved, and the near-perfect field creates a second problem which is in its way more immediate. One of the ways you determine how long a day is on a planet, how fast it rotates, is by tracking the rotation of its magnetic field. On Earth, the poles drift, but the field rotates with the planet, and you can measure that. On Jupiter, the tilted field sweeps through space in a recognizable pattern, and the rotation period is pinned to fairly good precision. But Saturn's field is so symmetrical that it barely varies as the planet spins. There is nothing to grab onto, no wobble to time. Cassini tried. The magnetometer data from the grand finale passes, threaded between the planet and the rings, gave the closest and most detailed measurement of Saturn's magnetic field ever obtained. And the answer was still at the end. We cannot pin the rotation period precisely. We have estimates, we have ranges, but Saturn's day, the exact length of a Saturn day, remains uncertain in a way that feels almost absurd given how long we have been studying the planet. It is, in its own strange way, one of the most human things about this mission. 20 years of travel, 13 years in orbit, 22 passes through the big empty, a final plunge into the atmosphere. And we still cannot tell you exactly how long a Saturnian day is. The universe is not obligated to give up its answers completely. Sometimes the mystery deepens. But let's come back to where we started, because there is still the question of where the rings came from. If they are young, if the leading interpretation is correct and they formed somewhere between 100 million and a few hundred million years ago, not 4.5 billion years ago, with the rest of Saturn's family, then something must have made them. They did not appear from nothing. Rings are debris, ice and rock and dust spread into a disk sculpted by orbital mechanics and gravity into the banded, structured, achingly beautiful thing Huygens identified from a 17th century telescope and Cassini documented in hundreds of thousands of images over 13 years. Something was shredded, or something collided. The two leading explanations are related. In both, the driver is a concept called the Roche limit. Every planet has one. It is the distance from a planet inside which the tidal forces, but the gravitational gradient across an orbiting body, the fact that the near side of the body is pulled more strongly than the far side, becomes stronger than the body's own self-gravity. Inside the Roche limit, a solid body held together only by gravity will be pulled apart, stretched, torn. A comet or an icy moon that wanders inside that boundary doesn't simply orbit. It disintegrates. It contributes itself to a ring. Saturn's rings sit, largely, inside Saturn's Roche limit. This has always been true. What Cassini's mass measurement changed is the timing, because for a long time the working assumption was that whatever made the rings happened early, that some primordial icy body got too close when the solar system was young and chaotic and being assembled, and the rings were the ancient debris of that ancient event. 4.5 billion years of rings grandfathered in from the solar system's violent youth. The mass is too small for that. The ice is too clean for that. So the shredding happened recently, on planetary timescales recently, when the solar system was already middle-aged and relatively settled. An icy moon of Saturn, Perhaps a moon now gone, perhaps something smaller, perhaps a comet that wandered in from the outer reaches and came too close, and the tidal forces of a planet that weighs more than all the other planets combined, except Jupiter, did what tidal forces do inside the Roche limit. It tore it apart, and from that fresh, clean debris, ice relatively uncontaminated by the long rain of interplanetary dust, because it had not been exposed for billions of years, because it had only recently been exposed, because it was new, the rings formed. Which means Saturn, at some point roughly within the last few 100 million years, may not have looked the way it looks in every photograph you have ever seen of it. May have been, if you had watched it from the right vantage point, just a planet, just an enormous golden gas giant, alone in its orbit, without the iconic structure that makes it instantly recognizable. The rings came later, they will go, we arrived in the interlude. That possibility is still debated. There are researchers who argue the rings might be older. The question of ring age is, in the way of most genuinely good scientific questions, not fully closed, but the Cassini results, the mass, the cleanliness, the composition, the rate of loss, pushed the weight of the evidence toward youth, and the leading interpretation now holds that we are seeing something temporary. Cassini proved the temporary. Cassini is also gone. There is something about that parallel that is worth sitting with for a moment. The spacecraft that returned the data showing the rings are temporary was itself temporary. It arrived, it orbited, it dove in its last months into the gap no machine had ever entered. It tasted the ring rain, it weighed the ice, it read the seismic record in the sea ring, it found the fuzzy core, it confirmed the ring rain rate, it measured the magnetic field's impossible near perfection. And then, on September 15, 2017, at approximately 11:55 UTC, it hit Saturn's upper atmosphere at a closing speed that turned it into light and heat and dispersed matter. The last signal reached Earth 7 hours and 55 minutes in the morning, Pacific time. The communication team in Pasadena had been tracking the signal throughout the final plunge, watching the data come back in real time. In situ measurements of Saturn's upper atmosphere, a data set that had never existed before because no spacecraft had ever been in that position before. Saturn's own atmospheric chemistry, sampled directly, not inferred from spectral observations made from hundreds of thousands of kilometers away. And then the signal stopped. Not a dramatic cutoff, not a final transmission, just the end of the data stream because the spacecraft could no longer hold its antenna pointed toward Earth against the atmospheric buffeting, and then because there was no spacecraft anymore. It was in the planet. It was Saturn. The team cried. Of course they did. 20 years is longer than some careers. Many of the people in mission control had worked on Cassini for so long that it was simply part of how they understood their professional lives. And when the signal ended, it ended for good. There was no Voyager-style ongoing data return to look forward to. There was no course correction available. The spacecraft was designed to die there. They had aimed it at the planet. And yet the grief was not the only thing in the room, because the data was there. It had been transmitted, most of it, over the years. The ring mass was measured, the ring rain was characterized, the age implication was established. The sea ring had yielded its seismic record, the Enceladus plumes had been sampled. Huygens had walked on Titan's surface, or more precisely, had settled into it, had transmitted for 72 minutes from the surface of a world 4 billion miles from the place it was built, the first landing ever made in the outer solar system. The mission was complete, the science was done, the spacecraft was gone. These three things are the same story. And here is the thing about that story that the eulogy frame tends to soften. The destruction was not the cost of the science. The destruction was the delivery mechanism of one of the science's most important findings. if Cassini had been gently parked into a stable orbit somewhere beyond the rings when the fuel ran low, the ring mass would not have been measured. The ring rain rate would not have been quantified in situ. The seismic record of Saturn's interior would be thinner. The fuzzy core might still be theoretical. The 30-year ring rain hypothesis would still be a hypothesis. The 22 orbits through the big empty, the trajectory that ended in the atmosphere that was designed to end there, were also the instrument. The suicide and the experiment were the same act, from the same trajectory, for the same mechanistic reason. Planetary protection forced the orbit inward. The orbit inward delivered the gap data. The gap data returned the mass. The mass revealed the age. The age confirmed the impermanence. The impermanence is what we are living inside of. An ethics decision, made to protect an ocean on a distant moon that the same spacecraft had discovered in 2005, an ocean that might or might not harbor something living, an ocean that a propellant-depleted spacecraft could not, in good conscience, be left to possibly contaminate, became the mechanism of a cosmological discovery. This is what the mission was, not just the photographs, though the photographs are extraordinary, not just the Titan landing, though the Titan landing was historic, not just the Enceladus plume, though the Enceladus plume may one day be recognized as one of the most significant discoveries in the history of planetary exploration. All of that is real, but the deepest thing Cassini gave us, in a sense, is the ring data from those last 22 orbits, the thing only possible because of how it died. And what that data says is this: you are looking at something temporary. The rings you see in the photographs, the rings that fill frames, that dominate wide-field solar system images, that seem as permanent as the planet they encircle, are a passing feature. They came from a catastrophe that happened by cosmic reckoning recently, and they are returning to catastrophe, draining into the planet they orbit, losing thousands of kilograms a second, not for much longer on the scale of things. In a few 100 million years, maybe sooner, depending on which estimates you weight, Saturn will be a planet without rings. That fact is vertiginous if you look at it from the right angle, because Saturn without rings is not Saturn as we know it. It is Saturn as something else, a gas giant like the others, distinguished by size and the amber color of its clouds and the peculiar near perfection of its magnetic field, and the strange fuzzy smear of its deep interior. But not that, not the rings. And for that brief window, 100 million years, give or take, that rings existed, we happened to be here. We happened to build telescopes. Galileo in 1610, squinting at what looked like ears, not knowing he was seeing the edge of a disk. Huygens in 1655, resolving the mystery as a ring. The Voyager flybys in 1980 and 1981, giving us our first real glimpse of the ring structures in anything like detail. And then Cassini, arriving in 2004, settling into orbit, spending 13 years mapping and measuring and sampling, and finishing by diving between the rings and the planet in the only trajectory that could weigh what it had spent years photographing. All of that happened in the eye blink, cosmically speaking, when the rings were there to be seen. We did not miss them. We were just in time. There is something generous about that. Something that feels, if you are in the right mood for it, like a kind of gift. Not one that was arranged, not one that implies anything about us or our significance in the universe. Just the bare, neutral fact that the rings and the humans overlapped, that Cassini was built in the overlap, that it arrived and orbited and died in the overlap, that the data came back in the overlap, and that you are here, wherever you are tonight, in a room somewhere, perhaps with a lamp still on, perhaps not, in the overlap. The rings are still there, right now, this moment. The light that would show them to you is traveling. Saturn is turning, slowly, with its rings intact, its C-ring still vibrating with the planet's internal oscillations, still recording the fuzzy core's strange seismic signature, still losing a few thousand kilograms of ice per second into the atmosphere below, still raining gently, inaudibly, invisibly into its own planet. You are in the window. That is worth knowing. That is worth carrying into sleep, if that is where you are headed now. There is a question that tends to arrive at this point in a story like this. Not a scientific question exactly, more of an orientation question, the kind that surfaces when you have been looking at the scale of things for a while and your ordinary sense of proportion has loosened a little. What does it mean that a robot built by people, built with metal and glass and silicon, powered by the decay of plutonium, carrying instruments designed to taste molecules, flew for 20 years to a ringed planet, orbited it for 13 years, and then dove into a gap no one had ever entered? And what came back was the proof that the rings will not last. The question doesn't resolve, it isn't supposed to. That kind of question is more like a direction than a destination. It points somewhere and you can look where it points, and what you see there is the very large and the very specific existing together. A planet 4 times Earth's diameter. A ring system that weighs less than half of a moon 400 kilometers across. A spacecraft the size of a school bus. A signal that took more than an hour to travel from Saturn to Earth. People in a room in Pasadena at 7 in the morning watching data arrive until it didn't. All of it temporary, all of it at some resolution, made of the same things, hydrogen and helium and ice and iron, and the particular arrangements of atoms that, in one configuration, make a ring, and in another make a hand that built the instrument that measured the ring. Cassini was made of matter from the same solar nebula that made Saturn. When it entered the atmosphere on September 15, 2017, it did not exactly leave. It joined. It became part of the planet it had spent 13 years studying. Its atoms are in Saturn now, not metaphorically. Actually, the spacecraft and the planet are the same substance, rearranged. The rings, when they finally finish raining into Saturn, will do the same thing. The ice that was once a moon or a comet or a wandering fragment of the outer solar system, scattered by tidal forces into the most spectacular ring system in this solar neighborhood, will become Saturn. Absorbed, incorporated, the temporary structure dissolved back into the permanent one. That is not a sad ending once you turn it the right way. It is just what matter does. It takes a form, holds it for a while, and then takes another form. The ring was the comet is the ring is the rain is the planet is eventually and impossibly distantly the next set of things. Cassini is Saturn now, and you, wherever you are tonight, in whatever corner of the world you have settled into, you are made of the same material. The elements in you were forged in stellar interiors before the solar system existed. The hydrogen that is part of your water is as old as the universe. You are not separate from any of this, from the rings, or the rain, or the spacecraft, or the planet. You are of it. That is what the science keeps finding, in one form or another. Every mission that pushes a little deeper, every instrument that tastes the atmosphere of a place no instrument has ever been, every measurement that overturns an assumption held for 4 centuries, they all converge on the same underlying strangeness, that this is all one thing, incomprehensibly large, achingly specific in its detail, and fundamentally continuous. The rings will go, Saturn will remain ringless in a solar system that will not notice. In a few billion years more, the sun will swell and change, and the solar system will become something else entirely. These are not reasons for sadness. They are just the shape of things, the shape that Cassini, in the last months of its mission, did something to clarify. We know now, more accurately than we knew before, that we are in the window, that the rings are young and temporary, that the number we can put on them, the mass, the drain rate, the remaining lifetime, changes what it means to look at a photograph of Saturn and see those rings curving away from the planet's equator. It means now. It means we happen to be here for this, and perhaps that is enough to bring into sleep with you if sleep is coming, not the sadness of impermanence, just the clean, quiet fact of having arrived in time, of being in the window, of the rings being there tonight, still falling slowly into the planet below them, still recording the planet's internal music in their structure, still catching the light of the sun 4 times farther away than the light we catch here. Back at the start of this, I asked you to hold one thought, that the death of the spacecraft and the discovery it returned were not 2 separate events, that they were one act forced by the logic of planetary protection and delivered by the specific geometry of a trajectory no one had ever flown before. I asked you to sit with that while we moved through the pieces. I hope it holds together now. The Enceladus ocean and the propellant depletion and the gap and the Doppler signal and the ring mass and the cleanliness and the rain rate and the Voyager hint and the 30-year confirmation and the seismic record and the fuzzy core and the perfect magnetic field and the unknown day all of it from the same decision made to protect something that might be alive that the spacecraft itself had found. A robot sent to look at a planet discovered a reason for its own destruction, and in being destroyed the way it had to be, proved that one of the most beautiful structures in the solar system is temporary. There is no moral to that, there is only the fact of it, and the fact of it is, in its own way, enough. If you are still listening, thank you, genuinely. This is a small, quiet corner of the night, and I'm glad you found your way here. If this kind of slow journey through the strange and enormous is something you enjoy, a like and a subscribe would mean a great deal. Small creators like me rely on your support to keep these going, and every one of them helps more than you might think. Tell me in the comments where you are listening from tonight, and what time it is in your corner of the dark. I read them, and I love knowing where in the world the night is settling in. The rings are still there. Saturn is still turning. The rain is still falling a few thousand kilograms at a time, carrying methane and ammonia and organic nanograins into the clouds of a gas giant that has been turning since before there were eyes to look at it. And you are in the window. The night watch has the dark covered. You can let go now.